Good morning. Happy Tuesday. I hope everyone had an amazing Easter weekend. Um, we're jumping right back in. I hope you enjoyed the little vector video I showed. I usually show that in class. I know if you were with me in geometry, you saw it when we did vectors in geometry, but some of you weren't with me in geometry, so um, welcome to vectors. Somebody told me, like, I never knew Vector was talking about math stuff. Of course he was. All right, so we're just going to intro beginning of 7.4 today. We're not going to try to get through it all because that's a lot of information. So we're going to kind of divide it out into a few days. So first things first, we need to get some basic information. Okay, vectors are what? It's a quantity that includes direction and magnitude. A vector has both direction and magnitude. If you were with me in geometry, we talked a lot about magnitude, but not a lot about direction. Okay, direction we're going to get into in trig right now more. If you remember, magnitude simply meant the what? The length or distance. Okay, the length or distance. But when we have both of these together, we have a vector. Okay, if you just have one, okay, if you just have one, a lot of things, there are a lot of magnitudes, okay? A lot of quantities include magnitudes, 45 pounds, 60 miles per hour, okay? If you have that, you have a scalar. They're called scalars. They're just the numbers, the quantities. Okay, quantities that involve magnitude. Okay, so it's like 20 pounds or 50 miles per hour. Okay, they don't give a direction. Okay, but now if you're saying you're going 50 miles east, that's a vector. Okay, that's a vector quantity. Okay. Typical vectors are velocity, acceleration, force. Yeah, we'll get a little bit into physics. You'll probably understand so much more than I do, but I know just enough to get by, okay? A vector quantity is often represented by a directed line segment, okay? So, if I were to draw a vector, it's going to go here. It's going to have an arrow on the end. It will look a lot like a ray. Okay, you'll have an initial point. We're going to call it Q, and an R is your terminal point. Wherever you're starting, that is your initial. A-L, sorry about that. Your initial point. Where you end, where the arrow is your terminal point. Okay? If sometimes we would use two letters, sometimes they're just going to give you a little one letter. They usually do an italicized. And they would say vector A. It would have a line with just the top part of the arrow over it. We would call that vector A. Okay. They usually do bold letters. Try to see. There's lots of words in this 7.4 that you probably should read. I probably should tell you all of it. I hit the highlights. The magnitude or the distance of vector A, they would represent the magnitude with absolute value. Okay? They want, when you see the little absolute value, that means they want the magnitude. Okay? How do we find the magnitude of a vector when it's just out there? Okay? Well, let's do that. I'm going to go to the next page. I'm going to actually put up a grid so that we can have a vector. And let's go ahead and draw a vector. I don't know which one is going to show. I don't like it facing that direction. Let's face the other direction. Okay? vectors don't really have necessarily a starting point. They're usually not on the XY plane. They're just out there, okay? But if you need to find the magnitude of vector, we'll call it vector V, okay? If we want to find the magnitude, we're putting our initial point at 0, 0, okay? So if I were to draw my invisible XY plane, I'm putting the initial point at 0, 0. Every time. If you remember in geometry, that's what we did. Every single time. And if I want the components, do you remember what the components were? The components of a vector are really, they talk about the horizontal distance and the vertical distance. So our horizontal distance, we're going over 1, 2, 3, 4, 5, 6. So my horizontal distance would be 6. My vertical distance, we're going up 2. It looks like coordinates, but we don't have parentheses on the outside. They're more like the greater than, less than symbols. So components are your horizontal and vertical distances from the initial point. Okay, those are your components, and it's always written like this. So if I wanted to find the magnitude, it would be written like this. Find the magnitude of vector V. Well, that can be also construed as the distance. Okay, they do a little blue, it's not blue, it's green. A little green box that talks about the magnitude, okay, of vector. They do a U, okay. If it has components, A and B, mine are 6 and 2, it will be the square root of, you could think about it like the distance formula, 6 minus 0 squared. This is going to be 6 squared. 2 minus 0 squared will simply be 2 squared. Okay? You could look at it like the Pythagorean theorem. Like it's a right triangle. You have 2 squared plus 6 squared equals the V squared. Okay? This is just taking the square root of it. Okay? So we would have the square root of 36 plus 4, so the square root of 40. Simplified radical, maybe 2 on the square root of 10. Okay? That would be a great magnitude. Okay? Can you find the direction? This is new in that box since I've jumped over there. Let's go ahead and find the direction. So here was our magnitude. The magnitude of a vector will be the square root of the components a squared plus b squared. Okay? If you want a definition, there's a good definition formula to put in there. Kind of all one color. I need to change colors. What if we wanted to find the direction? The direction is going to deal with your theta, your angle. Okay? So here we go. We have an angle theta that it's given. Okay? Now the question is, what pieces of this do we have? Do we have the opposite and do we have the adjacent? We're going to use tangent. To find the direction or the angle theta, so the direction is theta for tan theta equals 2 over 6, or in this case, A over B. No. It depends on which way you're going. I don't like to use these letters because I want to do 2 over 6 every time, whichever one is A and B. If this is A and that's B. Okay? Opposite over adjacent. That's what you have to remember. So we're going to do inverse tan of this. So in this problem, our tan theta would equal 2 over 6. So I would plug in my calculator, theta equals inverse tan, and I would probably go ahead and reduce it to 1/3. I'm going to pull up my calculator, which I have. Inverse tan of 1 divided by 3. And it's going to give me my angle, my theta, my direction is 18.4 degrees. Okay? And you're done. You have a magnitude and a direction. Okay? All right, let's go back. I've got just a minute. We're going to try to keep this fairly short. So I'm just kind of doing these first 2 pages. We have magnitude, we have direction. Can you take vectors and add them together? We did this in geometry. Yep, you're right. I'm going to go do another grid. If I have a vector, we're just going to do vector, stop right there, vector A and a vector B. So here we have vector, I'm not going to do A and B, I'm going to do U and a V. Vector U and vector V. And if I want to add them together, 2 different ways we could do this. One that we did in geometry, we find the components of each vector. So if this is my initial point, what is my terminal point? My vector U has components that are going to be what? So I count over 1, 2, 3, 4, 5, and I count up 2. It has components of 5, 2. Okay. My vector V has components of, I count over 1, 2, 3, 4, and I'm counting down this time, 1, 2, 3. If I'm going down, it should be negative. It was -3, not 4. Okay, so I went over 4 and down 3. Down is negative. Okay, and if I want to add my vectors, do you remember what we can do? We can simply add the components together. Okay? So if I add them together, A plus A, 5 plus 4 is 9. 2 plus -3 is -1. So that is vector U plus vector V equals 9, -1. When you add vectors together, we call that a resultant vector. When 2 or more, because you could add more, vectors are added together. Okay, that is a resultant vector. Okay, now in trig, we're going to have to do and remember a little bit more. We're going to have to know that I can see it visually. Okay, to see vector V, okay, we're just going to take the whole thing there. Okay, vector V and vector U, if you're going to add them visually, it's like taking the terminal point of one and putting it at the initial point of the other, or putting the initial point of V at the terminal point of U. Okay, so if I erase that dot, you can see terminal point of U is right with the initial point of V. Okay, so now my resultant vector should end at the final terminal point. Okay, so if I take from the initial, change colors, the initial point of U to the terminal point of V, how many did I go over? How many did I go down? I went over 1, 2, 3, 4, 5, 6, 7, 8, 9, and I went down 1. 9, -1. Is that what we got when we added them together? Okay? They call this the parallelogram rule. Another way to find the sum of 2 vectors is to use the parallelogram rule. Meaning, if I draw a line from the initial point of one to the terminal point of the other when they're lined up, that is my resultant vector. Okay? and I can draw a parallelogram around it. Okay? So if I wanted to do that, I feel like I'm already getting a lot of stuff on my paper. Okay? But vector V, would have to be across from vector V, 2, 3, 4, down 3. Okay? This vector over here that I just put up is a 4, negative 3. It's the exact same. It's an equivalent or an equal vector. Okay? And then if I did another U going up, over 5 and up 2, over 5 and up 2. Did I go over 5? Let's see, 1, 2, 3, 4, 5, and I went up 2. That's another vector U, not. Okay? So vector V and vector V are parallel to each other and they're equal. Vector U and a vector U are parallel and equal. The resultant vector is a diagonal that goes across them. Okay? Does that make sense? Well, we're going to stop right there. We're going to pause because I'm going over time. I'm going over a lot. And we'll come back again tomorrow. Great? A lot for one day. We'll see you tomorrow. Have a good afternoon. Bye.